respiratory system. As with the cardiovascular and the muscular, I'm not going to go over the anatomy. But that doesn't mean you don't need to know it, right? There's a rather splendid full-page copy of this diagram in the chapter. Anatomy questions won't be on the exam, but you need to know the terminology, you need to know the directional flow, things like that, otherwise the rest of what we are going to do won't click into place. Okay? What we're interested in particularly is what's going on at the level of the alveoli. All right, so down here at this level, the gas exchange is what we're particularly going to be looking at. All right, we'll do a little bit about how do we actually breathe, what's the mechanism for breathing, but most of what we're interested in is this gas exchange. How does oxygen get into the bloodstream? So the respiratory system has several functions. It's got to obviously get air in and out, and a big one is this exchange of gases between the air and the blood. So we're going to take oxygen in from the air to the bloodstream, and then we're looking to dump carbon dioxide out of the bloodstream into the air in the lungs and breathe that out. Okay? But it also has some other kind of less obvious functions in a way. It's responsible for humidifying the air. So when you breathe in through your throat or your nose, those have quite damp mucous membranes to try to add some moisture possibly to the air, particularly when we're living in New Mexico, right? Because we have so little moisture here. Our new faculty member, we were playing tennis on Saturday, and she mentioned how dry and how low the what's the word? Brain fart. Humidity. How low the humidity is, and I had to point out to her that it hasn't started really getting low yet. So she's got that to look forward to. She's come to us from Austin, so she's not quite used to the crinkly air yet. So we've got to humidify that air because the tissues, the lung tissue is very delicate, and it would get damaged very easily. We want to warm the air, particularly during cold weather, so that we don't take in a lot of cold air that sucks away from body temperature. And it's responsible for filtering the air. So one of the reasons we want to try to breathe through our nose more is that we've got these little cilia in our nose that can filter out some airborne particles, dust and things like that. And then that comes to the oral cavity and gets expelled. We cough and it comes out. So I don't know how you feel about it. My allergies have been so bad here lately, I feel like that system isn't working at all right now. Right? So our major role then is this gas exchange. Okay? Almost all that gas exchange occurs, let's go back here, at the level of the alveoli. There's a little bit occurring in the bronchioles. Nothing occurs on, breathing in and on its way down. All that gas exchange is occurring at the level of the alveoli. Okay. So if some airborne particles get missed on the way in, they are engulfed by macrophages, hopefully. If we had a little bit more humidity here, that would be easier for exercising, not as much as in the south. But here it is very dry, particularly in the winter. So it can be quite difficult for breathing and for people who are asthmatic, just because of the lack of humidity. All right, so you should know enough about the alveoli to follow. They're like little round sacs, little round balloons almost, and each alveolus, each balloon, is surrounded by a capillary network. So the blood-air barrier is very large. Right? They reckon that there's about 300 million alveoli in the lungs on average. And so there's this huge surface area between the capillary and the alveolus to perform this gas exchange, so that diffusion can take place there. If you laid out your lungs, if you opened all the alveoli up and laid them out flat on the floor, then again, on average, that's going to take up about the size of a tennis court, right? So it's like brain tissue, right? When you look at brain tissue, you've got all this wiggly, squiggly, because that allows for more surface area. Same thing here with the alveoli. The fact that we've got all these little round bobbles rather than just one piece of tissue allows for this massive surface area for diffusion. Okay? So we've got the membrane of the alveoli and the membrane of the capillary wall, and those two together are called the respiratory membrane. So we'll take a look at that on the next diagram. Okay? All right, so here, this is one alveolus, right? And you've got the pulmonary artery bringing blood from the heart that has very low oxygen levels and higher carbon dioxide levels, right? So the pulmonary artery then breaks into the capillary bed, wrapping around all these alveoli. So you can see this is blue, and then the capillary bed starts to turn red as it's picking up oxygen, and then all those capillaries run into the pulmonary vein, take the blood with the oxygen back to the left aorta so that it can be squished out with our cardiac output off around the body carrying oxygen. All right? And this is a cross-section of the alveoli, and you can see it's surrounded by capillaries. So, as I said, that surface area between the lungs and the bloodstream is very, very large to allow for as much gas diffusion as possible. Okay, here's the membrane of the capillaries, the red blood cell, right? And here's the membrane of the alveolus. And so we've got this very, very small distance of the respiratory membrane for oxygen to pass out of the lungs and onto the hemoglobin, and carbon dioxide to come out of the bloodstream into the lungs. Okay. So we have that's the wrong number for that figure, 7.3, okay. We want to, when we're looking at the mechanics of ventilation here, we want to remember our rule that we started thinking about in the last chapter, our high to low, all right? And remember I said it applies to gases, it applies to liquids, it applies to ions moving backwards and forwards across the membrane, okay? So high to low is going to play a role in what we're looking at here, okay? So we don't breathe exactly because our lungs get bigger and smaller, right? Our lungs can't contract. They don't have any contractile tissue in them at all. They're just flobby sponges, almost, right? So the way we breathe is due to pressure changes caused by changes in the volume of the cavity inside your chest. Okay? So we rely on the diaphragm and the intercostal muscles, a lot on the diaphragm. Okay? So what we see is that if we increase the volume inside the chest, then that decreases the pressure and that makes air rush in from the outside to the inside. Okay? Inspiration, I'm breathing in. But I'm not exactly breathing in, I'm just changing the volume of the cavity, right? And then the air outside is higher pressure than the air inside, and so we get movement of the air into the lungs. Right? Similarly, if we decrease the volume of this cavity inside our chest, that increases the pressure, right? So I've got a smaller amount of room with the same amount of air in there. So that increases the pressure, and it's now higher than the pressure out in the atmosphere, and so air moves out into the world. Expiration, I breathe out. So let's draw a little diagram for that. Hi, Chris.
Hey, Lucas, how you doing?
I'm good. I'm good. Okay, here we go. So, if my, how am I going to do this? Let's do this. If my intra pressure, right, inside is less than the atmosphere, then that equals inspiration, right? I breathe in. Okay. If my intra is greater than my atmosphere, then that equals expiration. I breathe out. Does that make sense?
Can you repeat it again for me?
Sure. Can you see this whiteboard?
Yeah, I'm seeing
Okay.
it.
So the pressure, the intra is the intrathoracic pressure. So the pressure inside the cavity in your chest, right? So within your rib cage, okay?
Yeah.
If the pressure in that space is less than atmospheric pressure, then we've got a high, low. So let me do this. Can I change this color? Yeah. Let's do this. This is then low, and atmosphere is high. So remember that we said when we were looking at the blood flow that it moves, that everything goes from high to low, right? So in this case, air moves from high to low, we breathe in, right? In this case, the pressure inside your chest is higher than the pressure outside in the atmosphere, and so the air moves out of your lungs into the air, and we breathe out. Right?
Yeah.
Got it? So
Yeah.
that inspiration, it's these inspiratory muscles, so the diaphragm, the intercostals, that increase the cavity volume. The diaphragm is the most important one, and it will, oh, I won't know on that one. It'll flatten. It'll flatten as it contracts. So the diaphragm, I don't know if you'll be able to see, let me see if you can see this. I'll turn the camera. Can you see George?
Yeah, I've seen George.
All right. So the diaphragm is this large, kind of almost like a flat rainbow-shaped muscle that sits up under your ribs and your lungs here. Right? And then under the diaphragm, you've got your liver and your stomach. Right? So it sits here. So when it contracts and it's joined to the ribs, right? When it contracts, it flattens, and that spreads your ribs out, right? Does that make a bit of sense? You can see, oh,
Yeah.
I'm putting his lungs in the wrong way around. That's not good, is it?
No, that's not good at all.
Poor old George. Oy. So it flattens. It flattens as it contracts, and that expands your chest, right? And then we've got these muscles that wrap around here, the intercostals contract and they pull your upper chest out as well. And then when we breathe out because we make the volume smaller, and so the diaphragm relaxes and comes back into place, and our muscles relax around our ribs, and everything shrinks back down, and that increases the pressure inside your chest. Okay? So this should say figure 7.3, not 6.3. It's the wrong. That's the wrong edition of the textbook. Technically then, the technical language would be that during inspiration and expiration, breathing in and breathing out, it's the pressure gradient that is created that changes by changing the volume that allows for air to rush in and air to rush out. Right? So now instead of having a gradient in the blood flow, now we've got a gradient in gases. But it's exactly the same idea. Everything goes from high to low. Okay? So resistance to airflow is exactly the same technically as resistance to blood flow that we looked at in the last chapter. It's the same principle. So instead of blood flow, we've got airflow, we've got a pressure differential from point A to point B, and the resistance. Right? So the resistance is the resistance to airflow between two places rather than the resistance to blood flow between two spots, right? So we can increase airflow then by making the pressure difference bigger and or by decreasing resistance to airflow. So in the same way that when we were looking at blood flow, we said the most effective way to impact blood flow is to change the radius of the blood vessels, right, to make it bigger or make it tighter. Same idea with airflow, right? The diameter of your airway is the biggest factor that affects airflow, particularly at rest. And then when we start to exercise, we see dilation of the bronchial tubes going down to the lungs, and that decreases resistance so we can get more air into the lungs when we're exercising. So what happens to people who have asthma, or who have, like we all have at the moment, these allergies that we're not sure why they're so bad this year, is that bronchodilation gets impaired, right? So I can't, when I try to exercise, I can't expand the bronchioles enough to get enough air in. And then we start gasping for air, or our chest feels tight, all those kinds of phrases that people use when they have asthma or when they've got allergy problems. Right? I don't feel like I can breathe and get the air in because the bronchodilation gets impaired. Okay? Some athletes will use those little nose strip things, nasal strips. That isn't shown in the research to really have an advantage at all. One thing you will notice, if next time you go out and you do something that's aerobic, try to pay attention to this because it's quite an interesting phenomenon. We go out and we know we're meant to breathe through our nose because it filters allergens, right? And so you start breathing through your nose. After a little while, you'll find you're breathing through your mouth, even though you meant to breathe through your nose. So what happens is your central nervous system wants more air, and your trachea is bigger than your nasal passages, and so it just flips, and it makes you breathe out through your mouth so that you're breathing in larger volumes of air. And if you try to not breathe in through your mouth and go back to your nose, it's actually really difficult to do. You should try it because your brain's telling you to breathe through your mouth. You're trying to breathe through your nose, and it gets very kerfuddled, really does. And then you feel like, oh, I'm not getting enough air in for the workload that I'm doing, right? So that creates a problem for people who do have allergies. It means that sometimes maybe they should exercise outside with some kind of filter mask or something like that. Or, like now, just don't take your mask off when you go and exercise. Who knows? Right, so if this bronchodilation isn't occurring, then that increases the resistance and decreases the airflow, means you have to use a lot more energy as well. So there's lots of negatives that occur if bronchodilation doesn't work well. If you're coaching athletes and they are using a puffer bronchodilator, it's important to check whether or not it's a steroid inhaler or just a bronchodilator. Because if it's a steroid inhaler and they get tested, then that can get them into big trouble. Okay? So that's something to watch out for depending what level you're working with. Okay, pulmonary ventilation. So we did a resting ventilatory threshold in the workbook the other week. So this is kind of links in with that idea of a ventilatory threshold. Pulmonary ventilation is the amount of air moved in and out of the lungs in a given time. So it's equivalent to Q in the cardiovascular system, right? Q is the amount of blood moved in and moved out of the heart within a minute. Pulmonary ventilation is the amount of air moved in and out of the lungs within a given period, right? Tidal volume is the amount of air that moves in and out per breath. So it's the equivalent of stroke volume in the cardiovascular system. All right. So volume of air moved per minute, same as Q, can be calculated as VE, which is air expired, equals VT, tidal volume, multiplied by F, which is breathing frequency. So the exact same equation as we had, Q equals heart rate times stroke volume. It's the same, just different letters because we're talking about gas instead of blood. Okay? It's higher in trained athletes generally. So for a sedentary male, VE is about 8 liters at rest to 113 liters per minute when they're exercising or walking, right? So for someone who isn't relatively active, we've got this 8 to 113 range between rest and physical activity. If you look at a trained individual, then the same idea as Q at rest, right? Rest is rest. If I'm not doing anything, I only need X amount of air. So 8, but it can go as high as 183 liters per minute. So much, much higher volume of air being moved in a trained individual than an untrained individual, all right? Genetics plays a bit of a role in that, but also training plays a role, right? But some people have larger lungs, for example. Some people will have a wider bronchial tube, just genetically, and that's just what they were born with. But training does seem to improve the amount of air that you can move in and out. Okay? Typically, we would have to measure this using a spirometer. When I was an undergrad, you had to use a Douglas bag. So it was this great big bag that was attached, and you breathed in and out, and the bag got bigger and smaller. It was very peculiar. Then they created a computer program to do that gas exchange. The spirometer in your mouth, the tube goes down and into the computer through a gas exchange module, and then the computer gets the data on oxygen versus carbon dioxide. So it's really pretty cool. And they got to the point where they can make the spirometer and the data gathering tool small enough to fit on a chest pack. So they're able to look at real world ventilation in athletes and others, but only if you're the kind of athlete where that chest pack doesn't, like, I don't think you'd want to have the chest pack on if you were playing a football game, right? But if you're a cross-country runner, you can put the spirometer in your mouth and have the chest pack on and go for a run, right? Or a biker. Okay? So when we start to exercise, we see a change then in this breathing pattern, which is quite interesting. So the first thing that happens is we start to breathe bigger, right? So we start taking bigger breaths to begin with after we start physical activity. If by taking bigger breaths, we meet our oxygen requirement for the exercise workload, then that's the adaptation you see. If, however, the bigger breath is still not providing enough oxygen for the end of that electron transport chain, right? Remember we said that that oxygen's got to be there to pick up the hydrogen. So if I'm not getting enough oxygen in, then we start breathing faster as well. But the rate of breathing is the secondary adaptation if the depth of breathing doesn't suffice. Does that make sense?
Yeah.
Yeah?
Yeah.
Okay. All right, so we said that the main role of the respiratory system is this gas exchange. So what are the variables involved that promote gas exchange, right, diffusion? So the first one is this massive surface area that we have, okay? The second one is how tiny that respiratory membrane, so the gap between the alveoli and the bloodstream. It's very, very small. Then we've got to look at the pressure of oxygen in the air and the pressure of carbon dioxide in the air, in the alveoli, and in the blood. When they use the term partial pressure, that means that, so if I look at the whole pressure of the air at sea level, that's made up of a certain amount of pressure of oxygen, a certain amount of pressure of carbon dioxide, a certain amount of pressure of nitrogen. We just never talk about nitrogen because it's like a neutral gas. We don't use it, we don't excrete it. It's got nothing to do with us. It's a plant thing, right? So we get the partial pressure of oxygen, partial pressure of carbon dioxide. Okay, and we'll come back to that in a minute. Dalton's law just says that the total pressure of the gas is the sum of all the partial pressures. I don't know how someone got to have that named after them. That seems logical to me, but anyway. Henry's law, another physics law, is that the amount of gas dissolved in the blood is going to depend on the temperature, the partial pressure of the gas, and how soluble it is. Okay? So, back to our high-low. Okay? So we're going to concentrate on the oxygen to begin with, all right? The partial pressure of oxygen at sea level is 159 millimeters of mercury, okay? So out in the atmosphere, that's the pressure of the oxygen. When we look inside the lung, the partial pressure is about 125, so it's lower there. And that allows air to move in to the lung, right? So the diaphragm contracts and flattens, our chest gets bigger, air can move in, okay? Now, the oxygen is great inside my lungs, but it's not helping me with energy production, okay? So we have to get it out of the lungs into the bloodstream. When we look at the blood coming through the pulmonary artery from the heart, and all of these are average numbers, right? Then the pressure of oxygen in the blood coming from the heart is about, I can't read that even with my glasses, about 40. So we've got a 40 and 125. Right? So there's a high-low, right? So that makes it very easy for oxygen to cross out of the lungs into the capillary network around the alveoli and back off to the heart. When we look at the oxygen pressure in the pulmonary vein going back to the left atrium, it's about 100. Right? Ooh, that's 105, not 125. So we've got 40 here, 105 here, 159 outside, and then 100 in the blood that's coming back to the heart. All right? So the high-low across the respiratory membrane drives the delivery of oxygen to the bloodstream. Okay? Round to the heart, into the left atrium, into the left ventricle, out to the left ventricle, around the body, we hit a muscle or another tissue or organ, right? Here we have partial pressure of oxygen of 100. We're going to assume that it's lower in the tissue because the oxygen can cross out of the bloodstream into the tissue. And then we've got our nice low 40 again. Where's that hand coming from? Our nice low 40 again, around back to the right atria, into the right ventricle, back to the lungs. Okay. So it can seem a little overwhelming when you look at that diagram, I think, because there's lots of numbers. They've got the numbers for oxygen as well as carbon dioxide. What you've got to remember is our high-low. Right? So let me draw a silly picture here to try to help. I need that up here. Okay. So, so my car is oxygen, right? If I park my car on a very steep hill and the handbrake fails, what happens to the car?
It slides down.
Slides down the hill, right? The steeper the hill is, the faster it's going to go down the hill. Agree?
Yeah.
Okay. If I park my car on a less steep hill and the handbrake fails, what's going to happen?
It's still going to go downhill, but just not as fast.
Right, it's going to roll down the hill slowly, hopefully, right? Good, okay. Third scenario then, what if I park my car on an absolutely level surface and the handbrake fails?
It stays.
It stays where it is, right? Nothing happens. So this is exactly what we're looking at on that other diagram. We're looking at pressure differentials or a pressure gradient, right? If the gradient is very steep, it's very easy for oxygen to cross the membrane. The less steep the gradient, the more difficult it is for oxygen to move across. And if there is no gradient, so if the pressure is exactly the same on both sides of the membrane, oxygen isn't moving anywhere. Does that make sense?
Yeah, that diagram helps a lot.
I love that diagram. It's very silly, but it works every time. Okay, so if you look at the diagram closely, you'll see that it's also talking about carbon dioxide, another gas, and that carbon dioxide is a output from aerobic ATP production, right? So when we go through Krebs cycle and we go through the electron transport chain, assuming we have enough oxygen there to pick up the hydrogen, we end up with water and we end up with carbon dioxide given off at other points, okay? So those two waste products have to be got rid of. The water's easy, the carbon dioxide is easy, it goes into the bloodstream. So if you look at this diagram carefully, you'll see that you've got oxygen with the arrow going one way and carbon dioxide with the arrow coming out the other way, right? So the capillary network around the muscle tissue, as it's leaving the muscle, is going to be lower in oxygen than it was coming in, but it's going to be higher in carbon dioxide than it was coming in. It picks up carbon dioxide. Right? And then that carbon dioxide gets to the lungs, and the pressure in the capillaries is about 46, but the pressure in the lungs is 40, and so carbon dioxide is able to cross out. It's not a very steep gradient, but it's enough of a gradient for carbon dioxide to cross over and get breathed out. Carbon dioxide in the atmosphere is 0.2 millimeters of mercury per 100, whatever. So there's a very steep gradient between the lungs and the atmosphere to get rid of that carbon dioxide. Okay? So I think I'm going to stop there, Chris, because that piece of information, that high-low and that gas exchange, needs some working through in your head. You need to spend a bit of time thinking about it, make sure you've got it.
Process.
Yeah, and make sure that you've got the right idea about the high and the low, right? Where is the pressure high, where is the pressure low? It's always going to go towards the low, right? So just play around with those ideas a little bit and let them soak in, because that will make things easier. I don't want to chuck something else at you now while that's all kind of fresh. I want you to be able to think that through while it maybe hopefully still makes a bit of sense. Okay?
Yeah.
All right. I've got office hours this afternoon if you need me. I've got office hours tomorrow afternoon if you need me. We will finish this chapter on Friday, and Monday will be a review session. So we go through this chapter on the respiratory system quite quickly. That's why I want you to kind of soak this bit in before I chuck the next bit at you. All right?
Yeah.
Okay. Have a lovely rest of your afternoon. Stay safe. And we've got lab tomorrow. I can't remember what we're doing. I have no memory. I don't remember what we're doing in lab tomorrow, but I'll jump into the classroom and have a quick chat for a while, and then set up some participation for worksheets and things. Okay?
Okay,
All righty, see you tomorrow.
all right, take care.